the recording now. Right, so this week we're going to look a bit at some applications of the operational amplifier. Last week we spent time looking at regulated power supplies and how we go about designing and making them. This week now we're going into the operational amplifier. I had put up a little handout, and there's some pages there that I ask you to look at. There's some little typos in it, but we'll figure out that as we go along. So specifically today, we'll start looking at, we'll run through some comparator circuits first off. And one of the things is that the operational amplifier, well, you know this, the operational amplifier has two inputs and one output. One negative, one positive, which is the inverting and the non-inverting inputs. Now those, because of the way that the op amp is structured, it makes it ideal for use in situations where you want to compare the voltage on one terminal to the voltage on another. And when that happens, if you, for instance, if you put some sort of a reference voltage on one terminal, then as the voltage on the other terminal varies, the op amp is going to switch from either its positive saturated output voltage to the negative saturated, or the other way around. Remember, again, because of the specs, it doesn't get quite to the plus or minus VCC, but depending on the op amp, it gets reasonably close. Now, this kind of comparative or comparator circuit allows us to create some interesting applications. And among them are the level detectors. And we're going to look at three over the next couple of minutes. One is a zero crossing detector. One is a positive voltage level detector, and the other one is a negative voltage level detector. So in the first case, the zero crossing detector. In this one, and let me zoom it up a little bit here, and you have this in your handout. Right, in the zero crossing detector, what we do is that we put the reference voltage, we make the reference voltage ground, 0 volts, and we use it either on the inverting input or on the non-inverting input, depending on what we want. If we put it here, now, first off, you might want to know, well, what are the sort of applications for that? Let's just discuss how it works first, and then we'll come into that, because we sort of touched on that briefly without realizing it last time. So here's what happens. I take a basic op amp, and I ground, in this case, I ground the inverting input. And I put a voltage, a varying voltage, right? Just for illustrative purposes, here I have a triangle wave on the non-inverting input. So what's going to happen here is that as soon as and I'll just call them the positive and negative inputs for the op amp, just to be easier to see. Nothing happens. I switch on the circuit. The instant the input on the positive, the voltage on the positive input to the op amp, meaning the non-inverting input, the instant that goes above 0, right, it means that the positive input here, as soon as that voltage exceeds 0, then the op amp immediately goes to its positive saturated value. The input voltage is varying, so it's above 0, then it starts to decrease. As soon as it crosses 0 and starts to go negative, then what happens is that the voltage at the inverting input is now more positive, if you like, than the voltage at the positive input. So the op amp switches state and immediately goes to minus VSAT. And then as of my input voltage changes again, the op amp switches and goes forward to plus VSAT. So in other words, it is, right now, all it is doing is detecting the zero crossing. Right, so every time, if you look at it, every time we cross 0, the op amp is going to switch from one state, either positive to negative or negative to positive VSAT. Here we have a little, I'll come back to the other diagram in a minute. Here we have what the transition looks like from minus VSAT to plus VSAT. And I'll just zoom in that before I come back here. If you zoom into it, you'll realize that when it changes from either negative VSAT to positive VSAT, of course VSAT meaning V-saturated, it doesn't do so instantly. There's a little slope to it. Right, there's a little slope to it. If the op amp was perfect, it would have done it straight up. But what it does is exaggeratedly, it looks like that. Two set of things you have to check. First off, the positive and negative saturation voltages, you get that from the spec sheet of the op amp. So inexpensive op amps like the 741, that is a good general purpose op amp, for instance, VSAT and minus VSAT may be within 1 volt, 1 to 2 volts of whatever VCC is. Expensive op amps and op amps that are designed for certain, let's say, medical applications or military applications or aerospace applications get much closer to VCC and will get within a couple of millivolts of VCC. It can't actually ever get there because of how the circuit is designed. There are diodes and transistors in the circuit that create the various voltage behaviors of the op amp. And because of that, it is impossible electronically for it to get to the supply voltages. But they designed them in such a way on the expensive op amps and on the very specialized op amps to get fairly close to it. The other spec has to do with how fast it changes from one extreme to the other. And that's where we come across this thing that you would have met before, something called the slew rate. Right? Now, the slew rate essentially is just a measure of how fast the operational amplifier can change from one state to another. And that has to do largely with the electronics, the actual electronic circuitry that is on the chip that makes up the op amp. Remember, these things are made of silicon, and all of the onboard components, there are resistors and diodes and transistors and so on that make up the op amp on the piece of silicon. And there's also in between junctions, and you might have met this before, in between the various junctions and the conductors of the piece of silicon, there are capacitances as well. They exist. There are something called parasitic capacitances, and then there are others that are there intentionally. Capacitors take time to charge and discharge. So in the end, the charging and discharging of capacitors, no matter how small it is, limits how fast any electronic circuit can move from one voltage level to another. Right? And those sort of things, again, the better the thing is designed, the more expensive it is because it costs money to compensate for these capacitances and the like, the more close to an ideal performance you're going to get. Right? If you need that kind of thing, and this is for design work and so on, you have to go back to the spec sheets. They give you things like the slew rate, they give you things like the VSAT, the V-saturation levels. Right? Okay, so it always is back to that. The manufacturers, and I mentioned that with the power supplies, manufacturers spend a lot of effort in documenting the characteristics of their designs because they have no idea what you're going to use it for, so they give you as much data as possible so that you can make use of it accordingly, depending on the type of application that you have in mind. So going back here now, so we see how it works. So I could put the reference voltage. The first diagram is where I put the reference voltage, which is 0 in this case. I ground the inverting input. And in the other case, I ground the non-inverting input. And the performance is just a mirror image of the previous case. So here, because I've ground in the non-inverting input now, once the inverting input is more than ground, it means that this is the active input. So the op amp is going to saturate at its negative value. As the input voltage decreases and it crosses back the zero threshold, it means at this point the positive input now becomes more, is more positive with respect to the inverting input. So the op amp saturates on the other end. And so you go. But it only is doing that at the zero crossings. Right? And this is the characteristic is the reverse of what we have on the mirror image, I should say. If you look at it, you just flip it around. That's what we have here. So the type of applications for this, why would you want to do that? Well, one thing, we mentioned this somewhere in passing in our conversation, either last week or the week before, is the question of detecting phases. How do you that we spoke about delays and phase when we were speaking about sinusoids, such as sine omega t plus phi, phase angle, and how you measure the phase angles. And somebody said, well, you look at the, you could kind of look at the zero crossing, and you measure that, which is exactly how you would do it electronically. So for instance, the reference voltage here doesn't have to be triangle. It in fact could be sinusoid. That's a very obnoxious sinusoid here. Let's do that a little bit better. Right, so sinusoid, try it again. Right, there we go. So it could be a sinusoid. So for instance, if I had, so this is my signal here. I could use these crossings here. Let's say I have more than one of these. So I have a signal coming in and I have more than one of them. So I have E1 coming in to one op amp and E2 coming in somewhere else. I could then look at the two outputs and both of them would give me a square wave depending on where the phase of the particular input was. So I could watch these sort of points here. And because I can measure that, which is getting very confusing here now, let me just put it here. So if I had two, just for argument's sake here, so let's say I had two of these. So one is giving me this particular input, and let's say the other one is giving me something looking like that. Right, so now I could look at this point here and this point here, and that time, if I know the time and I know the frequency, I could work out the radians, in terms of radians, how much that particular difference is. And that's how I would calculate a phase from it. Right, so you can use this sort of thing in a phase detection application, and it's not limited to just triangle waves. Yeah, fair enough. The saturation values, now I just mentioned that the saturation value, V out here, V out is a generic voltage value, but V out, sorry, wait a minute. The question was, is this the same as V out? Yes, correct. You remember the V out, this here. This is what we're measuring here. So V out is going to go between plus VSAT and minus VSAT. What it's not going to do is go between plus V and minus V. All right? Fair enough? Yeah? Nice. Okay. So here's another one now. Here's a positive voltage level detector. So instead of, now that we understand how it functions, if instead of putting the inverting or the non-inverting inputs to ground, we put them at some positive voltage, then we get this, the circuit, the V out of the circuit, we get V out switching now in where it crosses the reference instead. So instead of crossing 0 before, the reference points are now, the crossing points, sorry, the crossing points are right here. So every time it crosses the V reference now, that is the point where it switches, and depending on if you put the reference on the inverting or the non-inverting input, that will determine whether your voltage level detector switches to VSAT and minus VSAT, or the other way around. If you compare the top one, on the top one, once V in is more than the VREF, then it will go positive, because the positive input is now more positive. So it will saturate up V plus VSAT, and then when it goes below VREF, it will saturate, it will go to minus VSAT. The other way, the diagram below, I've put the reference voltage on the non-inverting input. So in the case of E in coming in now, when E in is less than VREF, then it's at negative VSAT. And when it increases, as it slowly gets above the, when it decreases and it gets less negative, then it flips the other way around, because it's on the inverting input. Why you would want circuits like that? Well, first off, you could think of it like protection circuits. We spoke about regulated power supplies last week. The power supply, we spoke about current limiting, but suppose you want to put something into a power supply that stops the voltage if the voltage gets above or below a certain value. Let's say there's a component failure inside or something, so on. Just to protect the output, you want it to shut off if the voltage got above a certain level. Then you can hook up a circuit like this. The VREF, of course, will be whatever is your set point for it, whatever is the level that you wanted to trigger at, and the E in will be the power supply output. So it's monitoring it, and then the instant that it exceeds whatever is the value that you had, it goes, the output of, in the case of the upper diagram, the output goes to minus VSAT. And if you tie that back to your pass transistor base, it's going to shut the power supply totally off. Okay, so it's that sort of thing. Another application is what I have, the last bullet here, and this is just one of many here. Something called PWM, or pulse width modulation. You all ever came across that, or the term? Right, so pulse width modulation, right, and you would meet it, again, you would meet it quite a bit in communications as you go about. Pulse width modulation is, straight off as the name implies, you have a system where you're using an input to modulate the width of a pulse. So you can think about it. If I have this, and let's say my E input, instead of doing this, if E input for some reason is varying, then what is going to happen is that at some points in time you're going to get a narrow pulse. In other points in time, like for instance here, you're going to get a much wider pulse. So the width of the pulse varies according to the frequency of the signal coming in. And they use that in communication circuits, in many communication circuits, to transmit information. It's a form of modulation. All right, and you're going to meet variations of that all the way through. Somebody mentioned in inverters, they also use it. Inverters are devices that take DC and give you AC, or try to give you a sort of AC signal coming out. And they use pulse width modulation to monitor, to regulate the load on the system, and also power amplifiers. Right, by changing the frequency, you change the duty cycle, right? So, and the same thing applies to certain types of power amplifiers. There are power amplifiers that work by modulating the output using pulse width modulation and then try to clean it up at the end. They're very efficient because all the output is doing is switching, or if you have transistors in a circuit, then all the transistors are doing are switching on at these points. They're fully on V saturated or minus V saturated in between. And if you think about a transistor, if the transistor collector emitter voltage, when it's on in full saturation, the collector emitter voltage is very small, so it dissipates quite a lot, quite a small amount of power compared to when it's in its linear mode. So you save energy at that point. Yeah. And then the flip side of this is a negative level detector. So instead of having VREF as positive, you have VREF as negative. And this is, again, is sort of the dual of the previous circuit. Again, you can use it, remember, like in power supply applications, again, protections, you have protection circuits, you have both V positives and V negatives in regulated power supplies. And again, you can use it for PWM applications. These are just some small examples of the types of things that you can use a level detector for. I don't know how many of you all have, for instance, appliance voltage detectors in your house, right? So what the appliance voltage detector is that if the voltage is, let's say, between 105 and about 120 or so, everything is all right. But if the power dips or it goes above that, the device switches off. You'll hear a click, and the power is disconnected until the power supply regularizes itself, and then you'll hear the relay click again, and it comes back on. Those will use voltage level detectors. You would have one for the higher voltage. You would have one for the lower voltage, and so once the voltage is somewhere in between there, the system does nothing. But if it goes above the higher one, it goes below the lower one, the system switches off. So there are any number of applications. As you read around and you look and you fiddle around with these things, you're going to find all sorts of applications for them. Yeah? So any questions on that? Most of the explanations are in the handout, but if you have any other things that are not clear. All right? And look, while you're at it, look at the transfer characteristics, okay? So pay some attention to these as well. Okay, look at them. Look on the positive level detector, the transfer characteristic is on the positive side. On the negative level detector, the transfer characteristic has gone to is on the negative side. Okay, so it shifts around a little bit. And of course, the 0 crossing 1, it is right on 0. Yeah, these are ideal cases. They really don't switch. So if you were to watch the spec for the op amp, exaggerated, it will look like that. But there's and they give you that sort of data for you to work with. So any questions? Yes, Jama. Yeah. Audio issues, you can type it if it's not too long a question. Okay, as soon as you can connect, just let me know and I'll just start.
Right, can you hear me?
Okay, yes, I am.
I wasn't sure if you went over this, but I was just kind of wondering why the reference voltage for EI or VI is at that height instead of the 0 volts reference that you had before.
Right. So where am I? This diagram, this particular one, or the which slide? This slide?
Yes, this slide is fine.
All right. Okay. So let me zoom in here a little bit. So you're asking about E input. So EI, so what we've done, we've set our reference at some negative value here. All right. EI is my input. That actually has nothing to do with the reference. Right? My EI is coming in. So this is what EI is doing. EI is symmetrical about 0. All right. So we're using that just to indicate how the detector works. It's a useful signal, and it's kind of like those the voltage. You remember when you were in year one, there were some op amp circuits that you had where you put a voltage on one input and you put a battery on another one, and you were trying to figure out what the overall output was. This is just a variation of that theme, except that we have a varying voltage coming in. But this voltage is presumably symmetrical about EI. That was just your assumption. Is that what you were asking?
Oh, I had thought that it was like offset or shifted up. Because you had a vertical line there, I didn't see that it was actually 0 at the reference
Yeah,
line.
right. So the inputs here, this line here, this is 0 here. Okay, so we're going symmetrically above 0, and I mean you could kind of gather that if I put a signal in on just a pure signal in on the op amp, there's no reason to assume that the signal would be something looking like this. All right. Not unless I deliberately want it to be like that. So what we have is a symmetrical signal about 0 here, and I put a reference now at this negative level here, and I just want to see how the circuit behaves. So at the point where it gets more negative is when the circuit will switch, and then anywhere else the circuit remains at positive VSAT. Yeah, that's all. And the point I was also making is that we use this just for convenience, but in fact, it can be, it could have been a sinusoid, right? It could have been some other sort of wave. For instance, it doesn't necessarily have to be triangle. Triangle is a nice linear varying waveform, but it doesn't have to be. You can use it to detect levels for sinusoids or the crossings for sinusoids in the case of the zero crossing. Fair enough?
Yes, sir. Thank you.
Okay. Right. The other applications we're going to touch on this afternoon are differential amplifiers. Now, there are many applications where you want to measure a voltage difference. You have some system, you have something going on, and you want to measure the difference in voltage between 2 points. But what you actually need to do is to also measure that in the presence of a large unwanted common mode voltage. So what does that mean, and what kind of application would that be? Take, for instance, something like this. We have a power supply and we have a load, and we want to monitor the current being delivered to the load. And how we do it is similar to what we did with the protection circuit in the power supply. We pass the current through a very small resistor, and we measure the voltage drop across the resistor. Right, so you're not passing current through any meter or anything, so you're measuring, so you're not breaking the circuit, but you put a sensing element in it, which is a small resistor, and we are going to measure the voltage drop across that resistor. If we know the value of the resistor and we know the voltage drop, of course, we could calculate the current. You're really not interested in, at this point in time, you're not interested in the voltage at these 2 points. What you really need to know is the voltage difference between those two. So both of them could be at some relatively high voltage. The voltage across this may be in the millivolt range, but each of these, for instance, can be like 10 volts for argument's sake. Here might be 10.1, here might be 10, right? So at this point in time, we have what is known as a common mode voltage. In other words, the information that we are interested in, which is the millivolt information, is sitting on top of somewhere between 10.1 and 10 volts, right? What we need is some way to ignore the 10.1 and the 10 and just pick up the little millivolt signal that is actually across Vx and Vy here. Yeah? Make sense? And you encounter that, in fact, in some other applications, like for instance, in medical applications, when they are measuring, for instance, when they put the electrodes on the body to measure, for instance, the heart electrical signals. Your body itself, because we are in an atmosphere that has a lot of electromagnetic radiation from, for instance, the power supplies in the wall, your body has a 60 hertz signal that is acts like an antenna, and that is there all the time. It's a very, very low power, but if you have ever held an oscilloscope probe in your hand and you watch your oscilloscope display, you're going to see, as you squeeze the probe with your fingers, you're going to see a 60 hertz signal appear on the screen. Okay, and it's worse again because you're not grounded, right? You're wearing shoes, insulating soles and the like. You have that signal inside of you. So when you stick, for instance, if there's a person on a bed and you stick electrodes onto them to measure the electric current passing through the heart muscle, the probes themselves are also going to pick up this common mode or this 60 hertz signal that is around the place, and it has to be good enough to ignore that and only measure the millivolt or the microvolt signal that we are interested in. So one way, back to the application, one way of measuring a differential voltage is using an op amp in a mode called a differential amplifier. Right? And you would have met this before, so it just we'll do a little review, but with some slight twist to it, so you can see some things that would not have come up the first time you met this when it was last semester sometime. So many situations require the amplification of a voltage difference. Two more here that I've put down is when you're measuring temperatures using thermocouples. In industry, for instance, they have very high temperatures to measure for many of the process variables. You can't put on an ordinary tight temperature measuring device. So what they tend to use are devices like thermocouples. Thermocouples are two sets of metals that are fused together. And when you subject the junction to a temperature change, it develops a very small voltage. So in industry, they use thermocouples all over the place, but it generates a very small voltage, so you have to amplify it. And the way you amplify it is by using a differential amplifier. Another one is a resistance bridge. You would have remembered from your physics and way back when, a good old-fashioned Wheatstone bridge. The Wheatstone bridge is how you would measure an unknown value of a resistor, for argument's sake. But you measure it by putting a voltmeter across the balance points, and you know the bridge is balanced when the voltmeter reads 0. Well, before you get to 0, you have to get to some very, very small voltage levels in the millivolt range, then the microvolt range, and when you can't detect it anymore, you kind of say that, okay, it's 0. So you need something to pick up a very, very small voltage between 2 points and amplify it, but ignore what the actual voltage is. And if you just as a sketch, if we remember that the bridge circuit, right? You remember what the bridge circuit looked like? You had one resistor, two resistors, three resistors, four resistors. You put the power supply You put the power supply across these 2 points, and then you measured the voltage between here. The resolution is poor, but you understand what I'm saying, right? Now, at the point, if all of these resistors if all of them are equal, right? And let's say my power supply is 10 volts. If all of these are equal, then the voltage between these 2 points is supposed to be 0. But the voltage here, just by some circuit theory, the voltage here and here is going to be 5 volts at each point, right? 5 and 5. So if I were to connect my op amp here, apart from reading the little voltage across here, the op amp, the non-inverting input, to be at +5, and the inverting input is also going to be at about +5 as well. That is what we call a common mode voltage. It has to ignore that. All right? So again, going back to what you did, you solve the what do you call it? The characteristic of the differential amplifier by using, I don't know if the term is raised there, but how you did it is that first off, you ground one input of the differential amplifier, and I'm using some different terms here. I think you may have used just R1, 2, 3, and 4, or have all equal or something like that. Just for our sake, R1 and 2 are the two input resistances. RF is for our feedback, where there's a feedback resistor coming in, and RG is the one going to ground, so it's easy to understand. All right? So you work out the input-output relationship for the differential amplifier by first grounding. Let Vin positive be equal to 0. So if Vin positive is equal to 0, we calculate what is the output due to Vin minus alone, and we get this is a basic inverting amplifier. And then we repeat the process, and we see what is the output. We ground Vin and then Vin minus, and then we look at the output due to Vin plus. And then we put both of them together, and we get the output is something related to Vn plus and something related to Vn minus. And why I'm doing that is because I'm interested in the difference between Vn plus and Vn minus. Right? You can follow the maths here. Normal, this is the normal inverting amplifier here. This is the normal non-inverting amplifier here. Okay? Fair enough? Everybody following so far? When you and just read the slides itself, nothing, no big set of maths inside of it, just some simple algebra. So at the end now, we get that the output of the differential amplifier is equal to something related to the voltage of Vn plus and something related to the voltage of Vn minus. Now, if I define my differential voltage, V diff equal to Vn plus minus Vn minus. In other words, I define my differential voltage as the difference between these two here. All right? Then, okay, so here it is. That's the first thing here. And then I make a couple of things equal. I make R1 equal to R2, and I just call it R, and I make RF equal to RG, and I just call it either RF or RG, so we just call it RF. Then the output of the differential amplifier is just the ratio of RF to R. Remember, this one is now, this is R, this is R. This, we make this, so this is RF, this is RF. The output of this now is V out is RF over R V diff, which is this, right? So this is V diff, right? Provided this happens here. Yeah? Fair enough? Everybody straight with that? Yeah, no, maybe. Okay, good. Again, a lot of this should be, well, most of this should be revision because I did derive this in 1011 last year. Right. So what we require now is that the measurement, the information that we want, is in this VDIF here. All right. This is the crux of the matter for us. That's the crux of the matter for us. VDIF. The absolute value of the potentials is immaterial. So we're not too sure, we don't care if this is just to be ridiculous, if this is 200 volts here and this is 207 volts, I don't care about 200 and 207. What I want is that the fact that the difference between the two of them is minus 7 volts. That is what I want out of that. So if you look at this thing, this whole something like this looks like it have a common mode, something common inside that they have about 200 all volts. All I'm interested in is the difference between the two of them, right? And the common mode voltage should not affect the measurements as we have no information in that we want. We don't care about the 200 and the 207. I want the difference, right? And again, I just put up the examples here. That now is where we're going to sort of delve in a little bit to how the system is designed to ignore one set of voltage, which is a common mode voltage, and what should I say, process the information that we want, which is a differential voltage, right? So right now, this is where we are. We just finished here. Get my marker here again. Yes, oops, keeps giving me some issues here. Right. So that in a box is where we just concluded the calculation. Let's change the inputs a little bit. So I have VDIF here, but I am also going to have a common mode voltage. This is the thing that is going to affect me that I want the system to ignore. And how I simply modify it, how I model it, just for the purposes of the analysis, is that I'm going to take VDIF and split it into two. So I have two voltage sources here. Each of them are VDIF over 2. All right. And right in the middle of the two of them, I'm going to add my common mode voltage. So if you go back to what we had before, if I have 200 and 207, right? Okay. What I'm saying here is that the difference between this thing is 7 volts. So what is this going to do? 7 volts, half of 7 is 3.5. So how this is going to behave for me is as though one input has 203.5, right? And the other one, one is going to go from 200 to 203.5, and the other one is going to go from 203.5 to 207. And inside, so the difference is 7 volts, but the common mode voltage now is being applied right in the middle of those two at the 203.5 volt, right? So if we do that, and again, this is just to make it easy to analyze. So VDIF again is the difference between these two voltages here. All right, VDIF is the difference between these two here. And V common mode, notice how I define V common mode. V common mode is the average of the two voltages here, right? So like before I had 200 and 207, so the average of that is 203.5. So the circuit therefore behaves as though I have a common voltage of 203.5 volts on each terminal. And then the actual input, the differential voltage now is the difference between the two, which is the 7 volts. Yeah? Just for calculation purposes. And what I do now, I'm doing this to lead up to something very important. This was the output voltage equation that we derived a little while ago. And we said, if everything is good, we make R1 and R2 equal, and we make RF and RG equal. I'm going to leave it like this for the time being, and you'll see why. So taking the little definition that we have inside of here, we're going to substitute V diff is V in plus and V in minus, and V common mode is V in plus V in minus over 2. So I'm going to go inside of here, and I'm going to manipulate and put in those values. So I'm going to put in these things in terms of V. So V in plus and V in minus, I'm going to express now in terms of V diff and V common mode. Fair enough? So I'm getting rid of the V in plus and V in minus, and I'm going to, in this equation, I'm going to change this equation so I have it in terms of V diff and V common mode now, right? And it's simple enough, because from here, like between these two, I could get that V in is something with V diff and V common mode, and V in minus is something with V diff and V common mode. You can work out the expressions, but it's right here on the slide. And if you do the substitution, V in plus is really V common mode plus V diff over 2, which makes sense. And V in minus is V common mode minus V diff over 2. So in other words, this minus V diff over 2 and this plus V diff over 2. Yeah? And now I expand this equation. I expand this entire equation here. And I group everybody with V common mode together. And I group everybody with V diff together. So when I do that now, I'm going to get that V out has two parts to it. There's a part with V out that is related to V diff alone, which is this bit here. And there's a part of V out that is also related to the common mode signal. Right? In other words, the gain, remember this is a when you calculate here, right, this is going to be some number, and this too is going to be some number here. So that the overall relationship between V out and V in, and V in has two parts, a common mode part and a differential part. There are two parts in it to that gain. And if you separate the two, we call the part that is related to the common mode part, that the V common mode, we call that the common mode gain of the differential amplifier. And the other part that is related to V diff, we call that the differential gain of the amplifier. So one is AV common mode, AV meaning there is a normal expression for voltage gain, and one is AV diff. Now, if the device works, or the difference amplifier, the differential amplifier works well, I have a difference amplifier, I have the word difference amplifier here. That's a term that you will also see appear from time to time, difference or differential amplifier. If it is really working well, it should, this part ideally is what you want. This part should be 0. In other words, it should ignore the common mode voltage, and it should only respond to the differential voltage. That characteristic is what we call the common mode rejection ratio, which is something that you would have met before, but we're doing it a little more formally here. And the common mode rejection ratio is the ratio of the the differential gain to the common mode gain. Ideally, this is supposed to be 0. So in a perfect op amp, an ideal op amp, the common mode rejection ratio is infinity. Right? As we can see now, because we're dealing with resistors in the circuit itself, it's not really 0, but it's something that we try to get down as close to 0 as possible. Now, many op amps, before you put it in the circuit, in other words, you're holding the chip in your hand, it has something called an intrinsic or a manufactured common mode rejection ratio that is usually very high, normally 80 decibels or more. decibels, remember, is a shorthand for is 20 log of two numbers, two ratios, and it's usually we do that instead of putting down a big long number, we convert it to something as a log scale. So 80 decibels, 20 log of the common mode rejection ratio is 80, so you could do the inverse log and see how big that is, and more. From the time you put it into the circuit now, once you put it into your circuit, right, you start to make the thing work, you have to put in R1, 2, and RF and RG. This device, the op amp itself here, has 80 dB of common mode rejection ratio in your hand, but you're now wiring it up with these four people here. And from the calculations before, notice that these now start to figure into the calculation. If RF is exactly equal to R2, if R1 is exactly equal to R2, and if RF is exactly equal to RG, then this comes out. These two factors, this minus this, is actually 0. And we're left with this, which is what we want. But as we will see, and we'll do this example tomorrow, resistors have a tolerance. The ones that you have in your kit has a tolerance of like what? 1%, 5%, 10%? What's right? If you're not sure about it, you have to look at the color band on it. Some are 5%, some may be 10%. Right. I don't think any of you all have 1% resistors, but the kit may have a combination of 5 and 10%. What we're going to look tomorrow, you could read ahead on the slides this afternoon if you like, or later on, is let's take now an op amp that has a nice intrinsic huge CMRR of 110 dB. I mean, you're holding it in your hand, it has 110 dB. I take what I think are fairly good resistors, which are 1%. And I put R1 and R2 here, they are 10K. They are 1% plus or minus resistors, and RF and RG are 100K 1% resistors. And the example that we're going to run through tomorrow is what happens if two of the resistors are on the high end of 1% of their value, so they plus 1%, and if the other two are lower than the normal value by 1%. Now, usually, just think about it. You have resistors and you're putting them in circuits. How many of you all actually measure the value of the resistor before you put it in? Some of you all will do because you didn't bother to learn about the color code, so it's a quick short way you put it on the meter and you measure it. But if you're trying to match the resistors, how many of us try to match the resistors exactly to what they're supposed to be? Not many. And we're going to look and see what the effect of that is come tomorrow. All right? We'll finish off this and we'll move on to our way around it in a little while. So any questions? We covered a fair amount and in a slightly different way than perhaps you would have covered it initially. So think about what we did is fairly straightforward analysis. Okay, no Laplace transforms or anything they like, no differential equations here, just pure, simple calculations here. Tomorrow we'll see what the effect is, and then we will go on to a better version of a differential amplifier, which is the instrumentation amplifier, and some other circuits after that. Yeah? Okay, so with that being said, I will end